welcome. So we're going to start chapter 12. We're going to talk about eventually vectors. But before talking about vectors in the space, first we're going to talk about the space itself. How do we define the distance, the metric space? How do we define sphere? And so on. So it's going to be all about Euclidean space. So we are in chapter 12, 12.1. We're going to talk about the space. So let's review a little bit. In intermediate algebra, in pre-calculus, we start defining Cartesian plane or rectangular plane. Rectangular. Let's talk about line, then rectangular plane, and then we continue that. From pre-algebra, line, then a rectangular plane, Cartesian plane. Now we're going to talk about the space. So when we have a line, this is our x-axis, or we have negative infinity to positive infinity. We have just one dimension. We say that R is equal to the real line, or the bolded letter R is equal to negative infinity to positive infinity. It includes all numbers on the horizontal axis. The dimension equals to 1. How is that? We say that, hey, you have R, and this R has not exactly the exponent. Informally, the exponent of R is equal to 1. The dimension is 1, and it includes all numbers on the real line. Remember that we define distance between two numbers as absolute value. So distance between A and B is denoted by absolute value of A minus B. Then we said that it's not very interesting for us. Let us construct something new, rectangular plane or Cartesian plane or xy plane, just a plane. Here we have x-axis, and we have another real line that we call, instead of saying that this is just x-axis, we call it y-axis. And now we have points in xy plane, like this point, 1 and 2, then this point, negative 1 and 2, this point, same, negative 1 and negative 2, and this point, 1 and negative 2. So we define it this way. We say we have R Cartesian product with R, and we denote it by R to the power 2. Again, this is informal. R to power 2, it's informal. It shows that the dimension is equal to 2, and it is defined this way. The set of all points, x and y, such that x and y are real numbers. So we read it this way. Rectangular plane is equal to the set of all points, the set of all points, x comma y, such that with the condition that there is this vertical line such that x comma y are real numbers. Then remember that we say that x and y divide the plane into 4 pieces, 4 sections. First quadrant, the second quadrant, the third quadrant, and the fourth quadrant. And we define the Cartesian plane or Cartesian product, or this is not cross, this is Cartesian product, which is denoted by r to the second. It means that we have 2 dimensions, which is the collection of all points x and y's, such that x and y are real numbers. If you want to graph this, you have to use a lot of dots, collecting all of those points representing this whole plane. And then we said that, okay, we have x, we have y. What about the space itself? How do you define the space? Space is defined as x-axis, y-axis, z-axis, and all points in the space. So our Cartesian product with R, Cartesian product with R, which is denoted by R to the third, is the collection of all triples, x, y, z, such that x, y, and z are real numbers. X, y, and z are real numbers. How did we define the distance in 2D? Distance between 2 points, A and B, and C and D. D is equal to square root of the difference between x value squared plus the difference between y value squared. The distance between 2 points in the space also defined as, so here, let me just separate these. The distance B is equal to, suppose you have this point, A, B, C, D, E, F is going to be the square root of the difference between x values, A minus B squared, plus the difference between y values, B minus E squared, plus the difference in Z values, C minus F squared. Very well. So when it comes to space, instead of having quadrants, we have octants. We have 8 sections or 8 divisions in the space, or we have 8 octants in the space. well. So let us talk about the graphing in the space. Suppose the question says, graph these two. It doesn't mention anything. Example. Graph the following. The first one says, hey, graph y equals to 5, and also graph x equals to y. Well, when it comes to graphing, you need to know which space you're working with. Is it a two-dimensional space or is it a three-dimensional space? In 2D and in 3D, we are dealing with different formats. For example, when it comes to y equals to 5, y equals to 5, in 2D, you have x-axis, you have y-axis, and you know that y equals to 5 is just a horizontal line. So y equals to 5 is a horizontal line. But when it comes to 3D, y equals to 5 is a plane. You have x, you have y, you have z. Y equals to 5 is a plane parallel to xz. So y equals to 5 is a plane parallel to xz plane. So this is our xz plane. It continues, but these two planes are parallel to each other. What about x equals to y? So in 2D, you all know this guy is just a line passing through the origin, and this is y equals to x or x equals to y. What about in the space? To visualize this in the space, let us use some online websites. So let us go to the website, Math 3D. Let us add an object. Let's see, what do we have here? So y equals to x. This is our plane in the space. Y equals to x. As you can see, it's not a line, but the projection of this plane in xy is a line that passes through the origin. But when you're looking at this in 3D space, it's going to be a plane passing through the origin. Very well. So we're going to use the definition of distance in our Euclidean space and write formula for the sphere. So recall that the distance between two points in the space, like x sub 1, y sub 1, z sub 1, and x sub 2, y sub 2, and z sub 2 is defined as d equals to square root of the difference between x coordinates plus the difference between y coordinates plus the difference between z coordinates squared, z1 minus z2 squared. Okay. Since we have the definition of distance, and we know how to define a sphere, I'm going to write down the formula for a sphere. A sphere is a set of points with the same distance from a fixed point that we call the center. So suppose you have a center and you want to write down the formula for the sphere. So let HKL, let H, K, and L be the center of a sphere. So here you have your space, 3D space, X, Y, Z, then, well, okay. Suppose this is your center here, H, K, and L. The definition of sphere is you have a set of points with the same distance from the center. So you have some points with the same distance from the center. The distance is the same. You have tons of different points in the space with the same distance. So the distance is the same. This point, this point, this point, this point, and the rest of them have the same distance. So this distance is fixed. Take a random point. Take a random point. This point has x coordinate, y coordinate, and z coordinate. So the distance between this point and the center is equal to x minus h squared plus y minus k squared plus z minus l squared. So what's the meaning of that? It means that b squared is equal to x minus a squared plus y minus k squared plus z minus l squared. And we name this r, we say that r squared, the radius squared, is equal to x minus a squared plus y minus k squared plus z minus l squared. This is the formula for the sphere. There you go. Now that we have the formula for a sphere, we might be able to have the formula for the sphere, but not written in nicer form. And they ask about the center and radius. So question says, what is the center and radius of the following sphere. Here we have x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equal to 0. So remember that when you're dealing with a sphere, it is x minus h squared plus y minus k squared plus z minus l squared equals to r squared. This is our sphere. But this way is written in expanded form. Let us rearrange these. Write all x terms next to each other, then y terms next to each other, and then z terms. So here we have z's. We have x squared plus 4x plus y squared minus 6y plus z squared plus 2z plus 6 equal to 0. Okay. This is in expanded form. What I want x minus a number into parentheses raised to the second power. I need x minus h squared plus y minus k squared plus z minus l squared equals to r squared. I need to complete this square. What I'm going to do, I'm going to add and subtract the constant that helps me to write this in compact form. This is x squared plus 4x plus 4 minus 4 plus, here I have y squared minus 6y plus 9 minus 9 plus z squared plus 2z plus 1 minus 1, and then I'm going to copy down 6 as well. This is equal to x plus 2 squared minus 4. Then I have y minus 3 squared minus 9. Then I have z plus 1 squared minus 1. Plus 6 equal to 0. So as you can see, we have x plus 2 squared plus y minus 3 squared plus z plus 1 squared. Here you have negative 4, and here you have negative 10 plus 6. So here you have negative 8 equal to 0. We have x minus 2 squared plus y minus 3 squared plus z minus negative 1 squared equals to 8. It means that we calculated the center you have square root of 8 raised to the second power. So the center is negative 2, 3, and negative 1, and the radius is square root of 8. Let's take a look at the graph. So let's add implicit surface. this side we have 0, and on the other side we have x squared plus y squared plus z squared. Then we have plus 4x minus 6y plus 2z plus 6 equal to 0. So let me just change this into the range that it's visible in all directions. You can also change this to 10 or anything that you like. Let's change the Greek. Okay. Let's get back to the board.